An important skill is knowing how to convert between position time graphs and velocity time graphs. The trick is that velocity is the slope of the position time graph. Let's do a couple examples. There are two related but slightly different strategies depending on whether the function is smooth or forms from straight line segments. In either case, the first thing I do is I want to make another set of axes for my velocity versus time graphs and put them right below. Now, it's really important to be able to do this that you line up the axes. So the first thing I do if I have a smooth x of t graph and I want to draw a v of t graph is I find the extrema. I find the places where there are maxima or minima. And I draw vertical lines going straight down to mark those points. Now, the reason I do that is at these points that are extrema, I know the velocity is 0. The next thing I do is I look at the regions on either side, and I look at whether the slope is positive or negative. So over here, the slope is positive, so that means the velocity must be positive. Over here, the slope is negative, so the velocity must be negative. And I also note that this slope is steeper than this one. So this distance must be smaller than this distance. And then I just smoothly connect those regions. And that's probably a pretty good estimate for what the velocity looks like given this position graph. The strategy that I use when it's a segmented graph is similar. I find all the breaks in the segments and draw vertical lines. And for these segmented ones, I'm able to be a little more quantitative, and I find that's actually kind of useful. So let's suppose that we have units on this, that we actually have labeled axes, right? And so suppose this is 0 meters, 0.1, 0.2. And let's make these times 0, 1, 2, 3. All right. And in a question problem, they'd have to give you these. You can, if you don't have those numbers, you can be qualitative instead of quantitative, just like I was here. All right. Then, for all of these straight line segments, you just calculate the velocity and draw it. So this one is easy. Velocity is 0. This one, the velocity is positive. And I go 0.2 meters in 2 seconds, which is 0.1 meters per second. Similarly, this one here, I go negative 0.2 meters in 1, 2, 3, 4, 5 seconds. Which if I do my arithmetic right, I think that's negative 0.04 meters per second. So for this part, I have a nice constant velocity that's positive. And for this part, I have a nice constant velocity that's negative. So this is pretty straightforward. We'll have lots of opportunities to practice. Now, you can also be asked to go the other direction. suppose you're given a velocity time graph and you're asked to get a position time graph. Let's just do a simple one where you have just a piecewise constant velocity. So again, the strategy is I copy my axes and I draw vertical lines at the appropriate breakpoints. Now, one thing is that from this graph, I can't figure out what the starting position is. So they have to give that, or it can be arbitrary. I'm going to choose my starting position to be right here. And now a constant velocity here means that the slope of this line is constant. And it's positive. A constant velocity is this thing means that the slope is now negative. And if I look, this is half as big as that, so I should have half the slope of what I drew here. And there you go. That's how you go from velocity versus time to position versus time. There are a number of other skills you need regarding converting from position and velocity graphs. For example, maybe you're given a position versus time graph and supposed to estimate the velocity at a particular point. So here's a nice sample x versus t graph. And suppose I want to know what the velocity is at this point here. Now, normally this is challenging in that you need to draw a tangent line to this point and then find the slope. Question is, how do you draw that tangent line? The way I like to do it is I like to take 2 points which are roughly equally spaced to either side of that point where we want to know the velocity, and draw the secant line instead. The nice thing about that is the secant line is unambiguous. It's just the line that passes through those points. So I like to find points that are roughly evenly spaced, and I also like to look at my grid lines and find points that are close to the grid points, because that's going to be easier for me to estimate the slope then. Okay, so for this particular example, here the rise is negative 0.1 meters. It's negative because I'm going downhill. And the run is 2 seconds. If 2 different students are doing this problem, estimating the slope, I wouldn't be surprised if they got somewhat different answers here. So someone else might get negative 0.06 meters per second. Someone else get minus 0.04 meters per second. Right? So this is not the sort of problem that has a unique answer. If you got negative 0.5 meters per second, clearly you've done something wrong. Right? So you need to get the right order of magnitude, but the exact number doesn't really matter for these kind of questions. The sign is really important. The fact that this is a negative slope, and the units are very important, which in this case, I need to actually give you the units on the axes for it to make sense. Yet another thing you might want to do from these sort of graphs is calculate the total displacement from velocity time graph. So let's actually reuse this one. Ask what is the total displacement? And for this, I'm going to have to put units on here. So let me do that. So this will be time in seconds. Let's do velocity meters per second. Because velocity is the slope of the position time graph, we can turn that around, and displacement is the integral of the velocity time graph. And actually, for a case of a time when you have uniform motion at constant speed, this is obvious. So for motion with constant speed, this statement is just saying that the change in position is velocity times the time interval, right? Which is just the definition of velocity. And this is just a fancy way of writing the generalization of that. So to get the total displacement, I have to find the area under this curve. And the rule is I need to take the positive of this and the negative of this, right? This is moving in the positive direction. This is moving in the negative direction. So I move forward here, I move backwards there. And this is just a nice rectangle. It has width 3 and height 2. And so this is 6 meters. And the meters comes about from, we have a meters per second here and a second here. Meters per second times second is meters. This one here, I have the height is 1 meters per second, and the width is 1, 2, 3, 4, 5, 6. So this is minus 6 meters. And so in this case, the total displacement is 0 meters. And in fact, we could also get that by reading off of this graph. Though generically, if all I want is the total displacement, you can calculate that without first drawing this graph. All right, let me conclude this video with one more thing you might want to do. And that is, you might want to estimate velocity from data, from position data, rather than from a graph. And the strategy we're going to use is exactly the same thing we use to find the slope from position time graphs. We're going to use that the secant line is a good approximation to the tangent line. So I'm going to take the secant line from these 2 points, the points that surround where we want to know the velocity. And the average velocity during that time interval is going to be a good approximation for the instantaneous velocity at the center time. All right, so I get that the velocity at time 2 seconds is approximately the distance traveled between time 1 second and 3 seconds and the time elapsed. And if I plug that into my calculator, I get 0.6 meters per second. Later, we're going to use the same approach with spreadsheets to, if I have a function defined by a position, or position versus time defined by some tabulated data, that I can create a curve of velocity versus time.